Hi all, welcome to the part 2 of today's lecture covering section 6.4 Green's theorem. So we talked about the three versions of Green's theorem, and for our purposes we are going to use the circulation form and the flux form, and we did few examples. So let's start with another example using the flux form of the Green's theorem. Example 42. Let S be the triangle with vertices 0, 0, 1, 0 and 0, 3. So let me draw the picture. 0, 0, 1, 0 and 0, 3. So we are interested in this triangle oriented clockwise. So the direction is clockwise direction. Goal is to calculate flux of this field across S. So S is the triangle. Okay. Now, if we were to find the flux using just the curve, then we have to do three integrals. So we have to break this S into three smooth curves and then find flux for each curve and then add them. So instead of that, we are going to use the Green's theorem. So we can only worry about the single double integral. So let's rename this region D. Now remember, Green's theorem says if the curve is oriented counterclockwise, we can do that. Now S is oriented clockwise. Right? So the flux is the integral over the curve S. Since it is oriented clockwise, we need to change its direction to use Green's theorem. Now remember, if you change the direction, then you should include a negative sign. Okay, now we can use Green's theorem to evaluate this part. Okay, so let's use the Green's theorem. We have the negative in front. This can be written as the double integral over the region D, and we are using the flux form. So it is P sub x plus Q sub y. Okay, what is P and Q? P is the first coordinate, Q is the second coordinate. So let's rewrite it. The double integral of the region D. P sub x is 2x. Q sub y is 1. Okay, now to do the double integral, we need to define the region D using variables x and y. D is the triangle, so it's a choice to pick which will be your independent variable. So let's go with x. X is in between 0 and 1. Then y, for a given x value, y goes from the bottom to top, 0 to the top curve, which is we need to figure out its equation. So it is the line joining 1, 0 and 0, 3. So it is y equals, the slope is negative 3, intercept is 3. So it is 3 minus 3x. So the region can be described as x in between 0, 1 and y in between 0 to 3 minus 3x. So the integral is negative x going from 0 to 1, y going from 0 to 3 minus 3x, 2x plus 1 dy dx. Okay, so you can take the 2x plus 1 out to the outer integral because it does not depend on y, and evaluate the integral. I'm not going to do it here. After evaluating the integral, you should get negative 5 over 2. Now it is 5 over 2 from the integral, and we already had a negative in front. Right. Okay, so we did a few examples using Green's theorem. Now let's try to extend Green's theorem to non-simply connected regions. Okay, so think about this region. So the region has a hole inside it, which means it's not simply connected. It's connected, so you can walk from any point to any other point without leaving the region, but it's not simply connected, meaning it has a hole inside. Now, the double integral over this region can be found using adding these two together. So, double integral over the upper part plus the double integral over the lower part. So, what we did is, we took a non-simply connected region and broke it into two nice simply connected regions. Now both parts are simply connected. Okay, now we can use Green's theorem for top and bottom separately. So we are going to use the Green's theorem to evaluate the top simply connected region. We can integrate that region. Instead of integrating across the region, we are going to integrate around its boundary in counterclockwise direction. Now, instead of integrating this bottom region, we can integrate the bottom part's boundary in counterclockwise direction. Now, the nice thing to notice here is the additional parts we add, they are in the opposite direction. In a sense, when you took them together, they cancels each out. So at the end, what we do is evaluate the line integral across the big circle in counterclockwise direction and across the smaller circle in the opposite direction, or in clockwise direction. So what we can do is we can extend Green's theorem to non-simply connected regions by finding the integral over the big region or the outer boundary, then subtract the inner boundary. Now, from this point onwards, we are going to use a convention. If D is the region we are interested in, then the boundary of D is the outer boundary. Let's say this is C, this is C prime. So it is the outer boundary minus the inner boundary, but the negative sign is already included because the direction is the opposite. So we use a convention. Boundary of the annulus D is C in counterclock. So outer bound in counterclockwise direction plus the inner bound in clockwise direction. Okay. Now you can actually extend this into more than regions with more than one hole. So let me quickly show that. So let's say you have a region with two holes. So the region we are interested in is this. What we can do is I can break this into two parts, the top portion and the bottom portion. The orientation is counterclockwise. Now when you put them together, the additional horizontal lines cancels each out. So what we are left with is the outer bound counterclockwise, the inner bounds in clockwise direction. So this can be done for non-simply connected regions with any number or any finite number of holes in it. Now you can use Green's theorem to evaluate integrals in this non-simply connected regions. So we can use the flux to get the idea or the intuition. Now remember, flux of a region is the amount going out of its boundary. So flux of the bigger circle is the amount going out of that region. So in blue color, I am drawing flux of the bigger circle. So flux of big or the outer circle is the things going out. Let's say arrows going out minus arrows going in. Let me use a black color to indicate flux of the small circle. The flux of the small circle is the arrows going out from the small circle minus the things coming in this small circle. So flux of the inner boundary or the small circle is arrows going out of the small circle minus the arrows going in. Now we are interested in this region, the region in between these circles. So we are interested in this annulus. Now the arrows going out of this region, this annulus region is, okay, so let's write flux of this annulus is arrows going out from the annulus minus arrows going in to the annulus. Okay, arrows going out from the annulus are the things going out from the bigger circle and things going into the small circle. So it arrows going out is out from big circle plus in to small circle minus. Now the arrows going into the annulus are the arrows coming into the big circle and out from the small circle. Into big plus out from small. Now out from big circle minus into big circle is the flux coming to the big circle, and the other two gives you the flux coming out from the small circle. So the total flux is the difference of fluxes of the outer bound and the inner bound. So that is the idea behind it. So basically we can use the Green's theorem, a slightly modified version of Green's theorem, even if you have a non-simply connected region. So let's look at an example. Example 46. Calculate the circulation given here, where D is the annulus given by the polar equation r in between 1 and 2 and theta in between 0 and 2 pi. Let me draw the picture. So r is in between 1 and 2 means circles of 1 and 2. Theta 0 2 pi meaning a full circle. So this is the region we are working on. So this is D. So boundary of D consists of outer boundary and the inner boundary. So boundary of D is let's say C1 plus C2, where C1 is the outer boundary, C2 is the inner boundary, and remember the outer boundary is counterclockwise and the inner boundary is in the clockwise direction. Okay, so we are asked to find this integral. Let me rename this as let's do this P, this Q. So we are asked to find the circulation. By the modified version of Green's theorem, this is the double integral over the region D, Q sub x minus P sub y. Q sub x is so derivative with respect to x is x squared minus P sub y is negative y squared, so becomes x squared plus y squared over the region D. Right? Okay, so instead of doing two integrals and then uh, subtracting them, you can now do a single integral, single double integral. Now the region is given in polar form, so let me write the region D is given in polar form, where r is in between 1 and 2, theta in between 0 to 2 pi. So let's convert this integral into a polar integral. 1 to 2, theta from 0 to 2 pi. X squared plus y squared is r squared. dA is r d theta dr. Yeah, now we can evaluate the integral. 1 to 2 r cubed dr, 0 to 2 pi d theta, and you should get 15 pi over 2. Evaluate the integral, you should get 15 pi over 2. Okay, so the use of Green's theorem here is, if you do not use Green's theorem, you will have to do two line integrals, one for the outer bound, then one for the inner bound. Take the reference. Instead of doing that, we can do a single double integral, which is not that hard to evaluate. Okay, so the last example for the day is example 40. So this is a modification of example 47. So I use example 47 prime. It says let f be given by this vector and C be any simple closed curve containing origin oriented counterclockwise. What is the circulation? Okay, so if you remember, this vector field represents a circular vector field with origin being infinite. So it is kind of like a hurricane. Yeah, when you come closer to the hurricane, the force or the field value increases, magnitude increases. Right? So therefore the zero or the origin is an undefined place. So the picture is, you can pick any closed curve, simple closed curve in counterclockwise direction. Now there is a bad point in the origin. So there is a bad point inside the curve C. Okay, so this is not a simply connected region. Therefore, what we do is, we are going to create, and actually there's a hint saying deform the curve to a known curve. Deform means change the curve. So let me change the curve into nice, let's say unit circle. And now this region is a nice region with a single hole in it. We can use Green's theorem inside this region, or the modified version of the Green's theorem inside this region. Now outer boundary is counterclockwise, inner boundary is clockwise. So outer boundary is C, let's say C prime is the inner boundary. Let's say D is the region in between. Okay, now the integral or the circulation over this boundary of D is equal to the double integral. So this is the Green's theorem over the region where you get q sub x minus p sub y dA. Okay, so we need to find p sub y, q sub x. What is p and q? P is the first component and q is the second component. P sub y, so differentiate the first component with respect to y, you should get x squared plus y squared on the denominator, x squared minus y squared on the numerator. So use the quotient rule. And q sub x, it's the same thing, x squared plus y squared on the denominator, x squared minus y squared on the numerator. Sorry. So the difference is 0. By using these two, we get difference is 0. Therefore, the integral value is 0. Right? Okay, so by using Green's theorem, we found the line integral along the boundary is 0. Now, the line integral actually consists of two things. So, the line integral we found is the integral of the region C, the curve C, plus the integral of the curve C1. Okay, so the boundary of D is actually C plus C1. Sorry, C prime. Right? And C prime, remember, C prime is in the opposite direction. Since this is equal to 0, we get what we need to evaluate is the negative of the integral along the C prime. Okay. Now, negative along C prime is you take the opposite direction of the curve. Okay, so what happened is we were asked to evaluate the integral along C. Now we change it to the integral along negative C prime. Okay, so it seems nothing much, but actually C is an arbitrary curve. C prime is the unit circle, which is nice and easy to evaluate. So C prime is the unit circle, so I can parameterize it using cosine t sine t, where t going from, so it's negative C prime cosine t sine t, t going from 0 to 2 pi, where r prime t is negative sine t cosine t. So this becomes 0 to 2 pi f. Okay, so now I need to plug x equals cosine, y equals sine to the function f. The function f has y over x squared plus y squared. By Pythagorean identity, x squared plus y squared is 1. And the second coordinate is negative x over y squared, x squared plus y squared. Dot product with the derivative negative sine t cosine t dt. Now we can easily evaluate this. Negative sine squared t minus cosine squared t dt, which is negative 1. So it's negative 0 to 2 pi, which is negative 2 pi. So what it shows is, if you have a hole or a bad point in the origin, it doesn't matter which curve you are integrating along, the answer is negative 2 pi. So if it is the unit circle, you get negative 2 pi. If you have some different curve, you still get negative 2 pi. Okay, that's it for this section. And tomorrow I will upload a video for the next section. And tomorrow we have office hours, so if you have questions, feel free to drop by. Have a great day.